Going to be working the solutions for L'Hopital's rule 3.7. So let's get started. There are a lot of problems in this section. All right, so number one, we're asked to find a limit. So we're back to limits again, but now we have the all-powerful, wonderful L'Hopital's rule. So what we need to do when we're using L'Hopital's rule is to make sure that when we apply the limit, we have either 0 over 0 or infinity over infinity. And here it doesn't matter if it's plus or minus there on top or bottom. One of those two forms we have to use the rule. Now, if I let x go to 1 here, we get 1 squared minus 1. The top is headed to 0. The bottom is 1 minus 1. That's going to head to 0. So we do have what we need for L'Hopital's rule. So I'm going to say that this is equal to, by L'Hopital's rule, the limit as x approaches 1. Then all we do is take the derivative on the top, which is 2x, and divide that by the derivative on the bottom, which is 2x minus 1. And now we apply the limit again. So let's let x approach 1. We get 2 on top, and on the bottom we get 2, take away 1, we get 1. So the limit here is 2. Now, what we could have done, just to show you, how we would have handled this before, is we would have factored the top as a difference of squares. We would have factored the bottom, GCF. We would have canceled these factors. And then we would have just plugged in 1 here. We would have got 1 plus 1 is 2. And here we would have plugged in 1. We would have got 1. 2 over 1 is 2. We get the same answer. But we were able to do that without using any algebra at all, just using the rule, L'Hopital's rule. All right, let's look at number 3. We have limit cosine goes to, limit x goes to pi over 2 from the right of cosine x over 1 minus sine x. So let's take a look here. Remember, pi over 2 is the angle straight up here. So cosine of pi over 2 on the top is the x-coordinate there. The x-coordinate here is 0, so we get 0 over 1 minus sine of pi over 2. Pi over 2, sine of pi over 2 is 1, so we get 1 over 1. 1 minus 1, which is 0 over 0. So we have what we need in order to apply L'Hopital's rule. So I'm going to apply it. Write the same limit down. The derivative of the top is negative sine x. And the derivative of the bottom, well, derivative of 1 is 0. Derivative of sine x is cosine x, but I have a negative in front of it, so negative cosine x. The negative over negative becomes positive, and we have sine x over cosine x. Now let's try this again. Let's see what happens. Or you know what, better yet, let's just rewrite this as tangent. I think that'll be a little easier for us to mess with. This is just tangent x. So it's asking what happens as you approach pi over 2 from the right on the tangent function. So for this, I'm actually going to go to the graph of tangent. If we graph the tangent function, it looks like this. And we have a vertical asymptote at pi over 2 and negative pi over 2. And then, so here's our asymptote here. And then what happens is it repeats itself. It does the same thing over here. Vertical asymptote here and here. So what happens on the tangent function is I approach pi over 2 from the right. So here's pi over 2 from the right. I'm on the tangent function. I'm headed towards negative infinity. So this thing goes to negative infinity, or here, negative infinity. Now we could have also got this by not turning it into tangent and just leaving it as this, and then looking at the unit circle again. And looking at pi over 2 again, that's the 0.01. Sine of pi over 2, that goes to 1. Cosine of pi over 2 goes to 0. So here we have fixed over 0. Anytime we have fixed over 0, remember we had three possibilities: infinity, negative infinity, or does not exist. And that's where you would have to like pick a sample point and approach it from the side and see what happens. But I think this was much easier just to look at the tangent function rather than to do the fixed over 0 part. Okay, next one. Limit x goes to 0. By the way, this is number 4. Limit x approaches 0 of sine of 4x over tangent of 5x. Now if x goes to 0, 4 times 0 is 0, sine of 0 is 0, so we get 0 on top. X goes to 0, 5 times 0 is 0, tangent of 0 is also 0. So we do have the appropriate form we need to use L'Hopital's rule, which I will do now. And this becomes derivative of the top, so be careful because we have 4x inside. So derivative of, it's chain rule, so derivative of sine of something is cosine of that something, times the derivative of what's inside, which is just 4, over, now the derivative of tangent of something is secant squared of that something, times the derivative of what's inside, which is 5. And now let's let x go to 0 again. 4 times 0 is 0, cosine of 0 is 1. So the top is going to 1 times 4, so 4, over secant squared of 5 times 0. 5 times 0 is 0. So I'm trying to figure out, what is secant squared of 0? Well, that's the same as 1 over cosine of 0. That's secant squared. Cosine of 0 is 1. 1 over 1 is 1. 1 squared is 1. So this right here is just going to 1 times 5. So 4/5. That's your answer. All right, number 5, limit t goes to 0 and e to the 2t minus 1 over sine t. So let t go to 0. 2 times 0 is 0. E to the 0 is 1. 1 minus 1 is 0. So the top is 0. And sine of 0 is 0. So we have the appropriate form we need for L'Hopital's rule. We apply the rule. Limit t goes to 0. Derivative of the top. We have two terms, right? Derivative of e to anything is itself. Chain rule says times derivative of what's up here. So derivative of what's up there is 2. And so we're done with derivative of e to the 2t. Minus the derivative of 1, which is 0. So that's it. That's all we have. Over derivative of sine of t is cosine t. Now let's let t go to 0. 2 times 0 is 0. E to the 0 is 1. 1 times 2 is 2. So we have 2 on top. And then cosine of 0 is 1. So we get 2 over 1, which is 2. There it is. Number 7. Theta goes to pi over 2. One minus sine theta over 1 plus cosine 2 theta. Just check to see what this was here. Okay. All right, so let's just check it. Pi over 2 is going to go in for theta. Sine of pi over 2, that's 1. We just did that on the unit circle a second ago. So we get 1 minus 1 on top. That's headed towards 0. Let's see. 2 times pi over 2 goes here. The 2's cancel. That's just pi. Cosine of pi. So go back here. Pi is here. That's our angle pi. Cosine is the x-coordinate, which is -1. So this right here goes to -1. 1 plus -1 is 0. So we have the appropriate form that we need for L'Hopital's rule. So I can apply it. Limit theta goes to pi over 2. And derivative of the top. We have two different terms. Derivative of 1 is 0. Derivative of sine is cosine. But we have a minus, so minus cosine theta. Over derivative of 1 is 0. And then be careful here because this is chain rule. We have cosine of something. Derivative of cosine of something is negative sine of that something times derivative of what's inside. Derivative of 2 theta is 2. And now we're going to try again. So theta goes to pi over 2. Cosine of pi over 2 is 0. Negative 0 is still 0. So we get 0 on top. And now let's try this. We're going to plug pi over 2 in right here. So if we plug in pi over 2 right there, 2 times pi over 2, we just get pi. And sine of pi is the y-coordinate over here. Oh, that's -1. Did I put -1 earlier? I don't know. It's supposed to be -1. I think I might have put 1. I don't know. Okay, sine of pi is going to be 0. So this whole thing right here is 0. And then times 2 is 0, so the bottom is 0. So we still have 0 over 0. And that means that the L'Hopital's rule did not fix it yet. Let's try and take the derivative again, or let's try L'Hopital's rule again, apply the rule twice. The reason we can apply the rule again is because we still have 0 over 0. If this came out to be something like, 4 over 2, or sorry, like 4 over 0, then we would have to do something else. But the fact that it's 0 over 0 means we can apply the rule again. So this is going to be equal to the limit as theta goes to pi over 2 of the derivative of the top. So derivative of cosine theta is negative sine theta, but then we have minus, so it's going to turn into a plus sine theta. Over, now on the bottom, remember this right here is really -2 sine 2 theta. That's what that is. Just move this 2 out front. And this is a constant. I'm going to be taking the derivative. It's going to come for the ride. -2 times derivative of sine of something is cosine of the something times the derivative of what's in here, which is another 2. And now I try again. So if I let theta go to pi over 2, sine of pi over 2, there's where we are. That's not where we are, sorry. Sine is the y-coordinate, so this is just going to be 1 over, all right, cosine of 2 times pi over 2, 2 times pi over 2, we've done this several times now, it's just pi. Cosine of pi, that means we're here, is the x-coordinate, that's -1. So this right here is -1. So I have -2 times -1, which is 2, times 2 again, this is 4. So we should get 1/4. That's it, we're done. So that's our first example where we had to apply L'Hopital's rule twice. Seems dark in here. Just make sure all these lights are on. That was number 7. Number 8's next. Just double check these lights. Ah, I thought there was a light off. Okay. Number 8. Limit as theta goes to pi over 2 of 1 minus sine theta over cosecant theta. All right, so theta is going to go to pi over 2. Sine of pi over 2 we already said was 1. 1 minus 1 is 0. So this is headed towards 0 over, now cosecant of pi over 2. So let me see what happens here. Cosecant theta is really 1 over sine theta. And if I plug in pi over 2, sine of pi over 2 is 1. So we should get 1 over 1. Let me see if I wrote that down right. Yeah? Okay, I'm just double checking this because we don't have to do anything here. Here's pi over 2. We got the x coordinate and the y coordinate. So sine of pi over 2 is the y coordinate, that's 1. 1 minus 1 is 0. Cosecant is 1 over sine. Sine of pi over 2, we just said is 1, that's 1 over 1. So this bottom part is just 1. 0 divided by 1 is 0. There's nothing to do here. There's no L'Hopital rule at all. So I think this problem is just to illustrate, don't go trying to do L'Hopital on everything, because if it's not 0 over 0 or infinity over infinity, you can't use the rule. And in this case, we just have a nice clean answer and we're done. All right, number 9. Limit x approaches 0 from the right. Of natural log x over x. All right. So let's see what happens here. What happens to the natural log function as we approach 0 from the right? So let me graph the natural log function. Natural log function looks like this. So as we approach 0 from the right, this heads to negative infinity over, and then the bottom is headed towards 0. And it's coming in from the right, so it's little positive numbers. So what happens here? There's two ways you can look at this. Well, here's one way. You can rewrite this as 1 over 0 times negative infinity. So just kind of like sliding this off to the side. And we can ask ourselves, okay, what happens if you have a fixed number that's positive, 1 is positive, over a number that's getting smaller but is also positive? So remember, if you have fixed over 0, that's going to be infinity, negative infinity, or does not exist. In this case, since the numerator and denominator are both positive, this is going to go to positive infinity. If you take a huge positive number, right, and multiply it times a very huge negative number, you're going to get a very huge negative number. So you're going to get negative infinity. So this is another illustration where we did not use L'Hopital's rule. In fact, we could not use L'Hopital's rule because we did not have what we needed. All right, number 10. The problem with L'Hopital is that people will start getting like so happy about it that they just start doing L'Hopital on everything, and you can't. All right, limit as x goes to infinity of natural log of the square root of x over x squared. All right, so what happens if I start letting x go to infinity here? This gets huge. Square root of infinity is still infinite. Natural log of infinity means, if we look at the natural log function, which we just looked at, what happens is we start going out this way. What happens to the natural log function? Well, it starts to grow without bounds, so it becomes infinite also. So the top here is headed towards infinity. And then, of course, infinity squared is going to be infinity, so we get infinity over infinity. We are allowed to use L'Hopital's rule because we have this. So I'm going to bring in L'Hopital's rule. And I guess I could just use L'Hopital's rule right now. Take derivative of the top and the bottom separately and figure out what it is. But I realize I'm going to have chain rule on that. So what I'm going to do first is I'm going to rewrite this. as natural log of x to the 1/2. That's what that means, because square root of x means x to the 1/2. Then I'm going to use property of logs to pull the 1/2 out. And so that is the top rewritten. That's this rewritten. And now I will take a derivative. The derivative of this, the 1/2 comes along for the ride. The derivative of the natural log of x is 1 over x. So that's the top. And then the bottom we have just 2x. Now let me try and clean this up a little bit, because I've got kind of like a little complex fraction here. Got 1 over 2x is the top, over, the bottom is 2x over 1 if I want to look at it like a fraction. That way I can write a fraction over a fraction. And then I flip reciprocal, so limit x goes to infinity of 1 over, so this flipped and became 1 over 2x here, multiplication, that's gone. And that gives us 4x squared. And now if I let x go to infinity, I have a fixed number on top. The bottom is getting huge. So in a fraction, if the top doesn't move and the bottom gets big, the fraction gets small. This approaches 0. All right, my phone's going off here. Let me see what this is all about. Okay, I've got to remember to get back to that. All right, where are we at? Number 11 now? Yeah. Limit t goes to 1. T to the 8th minus 1 over t to the 5th minus 1. All right, let's let t go to 1. 1 to the 8th power is 1 minus 1 is 0. 1 to the 5th power is 1 minus 1 is 0. So we have what we need for L'Hopital. T approaches 1. So I take the derivative of the top. Derivative of the top is just 8t to the 7th. Derivative of the bottom is 5t to the 4th. And let me keep going here. This is, I'm going to just algebraically clean this up. This t to the 7th over t to the 4th is t cubed. So I have 8/5 t cubed. And now I go ahead and take the limit, let t go to 1, t cubed is, or 1 cubed is 1, times 8/5. The answer is 8/5. That's where it's headed. That was pretty clean. Limit t goes to 0. Of 8 to the t times 5 to the t, or minus 5 to the t over t. So let's let t go to 0. 8 to the 0 is 1. Minus 5 to the 0 is also 1. Over the bottom is headed to 0. So this is going to 0 over 0. So that's where it's headed. I can apply L'Hopital's rule. Limit t goes to 0. And let me be careful with these derivatives. The derivative of 8 raised to the t, that's an exponential function, is itself, and remember this from class, times natural log 8. So this is the one where we had like a raised to the x. The derivative was itself times natural log a. So that's what I'm using there. Then I have minus, this is another exponential function, so the derivative of that's going to be 5 to the t times natural log 5. All of this over the derivative of t, which is just 1. And this should be good, because now if I let t go to 0, 8 to the 0 is 1 times natural log 8, minus 5 to the 0 is 1 times natural log 5, so I get natural log 5. And I'm sure the back of the book is going to have this written instead, because they're just going to use property of logs. Subtraction between two logs becomes a single log with division. So they just condense it down, and we're done. (13) Limit x goes to 0. E to the x minus 1 minus x over x squared. X goes to 0. E to the 0 is 1. 1 minus 1 is 0. Minus 0 again. The top is headed towards 0. And the bottom, of course, 0 squared is 0. So we get 0 over 0. We can apply L'Hopital's rule. Derivative of e to the x is itself. Great. Derivative of negative 1 is 0. Derivative of negative x is negative 1. Over derivative of x squared is 2x. I apply the limit again. X goes to 0. E to the 0 is 1. 1 minus 1 is 0, so I'm headed to 0 on top. On the bottom, 2 times 0 is 0. So I have 0 over 0 again. That's fine. I'm going to apply L'Hopital's rule again. Derivative of e to the x is itself, minus derivative of 1 is 0, so there's nothing there. Derivative of 2x is 2. And now let x go to 0 again. So e to the 0 is 1, 1 over 2, that's just 1/2. I'm knocking these out. All right, number 14. Limit u goes to infinity of e to the u over 10. I'm going to rewrite that as 1/10 u, right? U over 10 is the same as 1/10 u. And then over u cubed. All right, let's let u go to infinity. 1/10 of infinity is still infinity. E to the infinity means, if you look at the exponential function, what happens as you start going out to infinity here? Well, the function obviously starts going up to infinity. So the top is headed towards infinity, and then the bottom, infinity cubed, is still infinity. So you have infinity over infinity. So we'll do L'Hopital's rule, because we can. L'Hopital. Derivative of e to anything is itself. Times chain rule here. We have to take derivative of what's up here. The derivative of what's up there is 1/10. Over derivative of u cubed is 3u squared. And then we try again. U goes to infinity. We already said that this will go to infinity. Infinity times 1/10 is still infinity, so we have infinity on top. Infinity squared is infinity, times 3 is still infinity, so we have infinity over infinity. Let's do L'Hopital again. Derivative of e to anything is itself. Chain rule says times derivative of what's inside. And I didn't mention this, but the 1/10 was a constant, so it was just going to come for the ride, so there's another 1/10. All over derivative bottom, which is 6u. And hopefully you picked up on the pattern here. What's happening is that every time we do this, we get infinity over infinity, right? We got infinity over infinity here. Here we're going to get, again, infinity times 1/10 times 1/10, still infinity, over, look, 6 times infinity, still infinity. So we keep on getting infinity over infinity. However, the denominator keeps going down by a power each time. And the numerator, I just keep on getting the e to the 1/10 u every time. It's not going to go away. but the power on the bottom will start to go down eventually. Let's see here on the next line. When I do derivative on top again, this is a constant, it's going to come for the ride. I'm going to get e to the 1/10 u times 1/10 times 1/10 times 1/10. I could just do 1/10 cubed and I can make that a 1/1000th, but I'll just leave it. The derivative bottom is 6. Now the denominator is no longer going to infinity. The numerator, however, is. That's infinite times all this. So what you have here is like infinity over 6, and that's still infinite. So your answer here is that it is infinite. Okay. Let me go check the time on this video. 30 minutes. In about 15 more minutes, I'll go till 10 o'clock. Limit. X goes to 0. X times 3 raised to the x over 3 to the x minus 1. All right, let's just check to see that we have what we need here. X goes to 0. 0 times, let's see, 3 to the 0 is 1, so 0 times 1 is 0. The top's headed towards 0. 3 to the 0 is 1. 1 minus 1 is 0, so we get 0 over 0. Wonderful. It's okay, L'Hopital. L'Hopital. All right, I have to take derivative of the top. Product rule. I think that's the first time we've had that happen. Derivative of the first one is 1 times the second one plus the derivative of the second one, that's an exponential. So derivative of 3 to the x is 3 to the x times natural log 3, don't forget that part. And then times the derivative of the first one, times the first one, which is just x. So there's your product rule up top. And then derivative of the bottom, 2 terms, that's going to be 0. Derivative of 3 to the x is itself 3 to the x times natural log 3. All right, well, it looks like at this point you could start letting x go to 0 again, but let me just clean this up. Notice that in the numerator I have 3 to the x here and 3 to the x here. So I could factor out a 3 to the x, and I would have 1 plus x natural log 3. So I pull this 3 to the x out, there's a 1 there, pull that one out, and I have these two pieces here, which is this, all over 3 to the x times natural log 3. These cancel. And now I let x go to 0. If that's 0, that's gone. I just get a 1 on top, 1 over, and then natural log 3. Okay. 1 over natural log 3. Interesting answer. Limit x goes to 0. Cosine mx minus cosine nx over x squared. All right, so let's do this. X is going to 0. M and n are constants here. Some number times 0 is 0. Cosine of 0 is 1. Some number times 0 is 0. And then cosine of 0 is 1. So 1 minus 1 is 0 on top. And on the bottom, of course, 0 squared is still 0. So we can do L'Hopital. All right, we got to be careful here. Derivative of cosine of something, right, chain rule, is going to be negative sine of that something times the derivative of what's inside. The derivative of mx is m, right? If that was a 5x, it would be 5. If that was 10x, it would be 10. So since it's mx, it's just m. Then we have minus the derivative of cosine of something again, which is negative sine of nx, times the derivative of what's inside, which is n. Now I put the parentheses here because I'm going to have a double negative, so it's just proper notation. Then all of this over 2x, derivative of the bottom. All right, I'm going to change this. I'm going to take this parenthesis off. Take this parenthesis off. Make that a plus here. And now let's let x go to 0. We get here 0, right? 0 times m is 0. Sine of 0 is 0. So this is 0 here. Same thing here, that's 0. Sine of 0 is 0. 0, the whole thing here. 0 plus 0. So we have 0 on top. And on the bottom we have 0 also, if we let x go to 0. So I'm going to have to do L'Hopital again. L'Hopital. L'Hopital. All right, this is a constant. You could look at this as being like a negative m out front. It's just going to come for the ride. So here's my negative m. I'm bringing it along for the ride. Times derivative of sine of something is cosine of that something. But then chain rule says derivative of what's inside, which is just m. All right, here I have an n is a constant. It's going to come for the ride, so I'm going to say plus n. Now derivative of sine of something here is cosine something, times derivative of what's inside, which is n. All of this over 2. Derivative of 2x is 2. And now I will let x go to 0. So if x goes to 0, this is cosine of 0. Cosine of 0 is 1. So I'm going to have negative m times 1 times m. That's negative m squared. And then I'm going to have cosine of 0 again, which is 1, and then I have n times n, that's going to be plus n squared, all over 2. There you go. That's weird. It's a general answer, because we don't know what m and m are. M and n are. Our answer is going to be in terms of m and n. So if someone gave me like an m and an n in there, then I would have an answer. Limit x goes to 1. One minus x plus natural log x over 1 plus cosine pi x. All right, let's let x go to 1. 1 minus 1 is 0. Natural log of 1, you better know this. Natural log of 1, here's natural log. Natural log of 1 is 0. So 1 minus 1 is 0 plus 0, that's 0 on top, over, let's see, this is pi x. If I replace this with 1, this is pi. Cosine of pi, pi's over here, cosine's the x coordinate, negative 1. So this is negative 1. 1 plus negative 1 is 0. So we get 0. 0 over 0. L'Hopital, 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 L'Hopital. All right, derivative of the top. 0. Derivative of negative x, negative 1. Derivative of natural log of x, 1 over x. Done on top. Derivative 1, 0. Derivative of cosine of something, negative sine of that something, times derivative of what's inside. Derivative of pi x is just pi. Let x go to 1 again. Uh-oh. X goes to 1. 1 over 1 is 1. Negative 1 plus 1, that's 0 on top. Uh-oh. Okay. Pi here, pi times 1, that's sine of pi. I'm trying to figure out what sine of pi is. We just did that on that unit circle. It was over here. That was a 0, so it's going to 0 at the bottom. Okay, well, got to do L'Hopital again. I'm not feeling good about this. Looks like it's going to get a little bit messy here, but we'll see. All right, derivative of -1 is 0. Okay, derivative of 1 over x. Remember, 1 over x is really x to the -1, and if we take the derivative, it's -1x to the -2, and that's really -1 over x squared. Okay, I've done that enough, and I think you can follow that if you just pause the video and look at it. That's that. So, derivative of this, -1 over x squared, over. Ooh. Okay, pi here, negative pi, that's a constant. It's going to come for the ride. Derivative of sine of something, right? I've already taken care of the negative and the pi. Derivative of sine of something is cosine of that something times derivative of what's inside, which is pi again. And now I hope for the best here. If x is 1, this is -1 over 1 squared. That's -1 on top. So that is headed towards -1 on top over, see, cosine of pi times 1, that's pi. Cosine of pi, we said that was -1. So this was -1. So negative pi times -1 is pi. Then times pi again, that's pi squared. Oh, that's it. L'Hopital is awesome. $19. This will be my last one. Well, maybe not. You know what? I'll be right back. I can't pause it. Well, I guess I could stop the video. Let me stop the video and then I'll start over again.